Okay, so what are some things you notice in the problem? At least 5 pounds. What?
We still use mu1 and mu2 here,
right? Yes.
Okay. So wouldn't that be the mu1 is greater than or equal to mu2?
Well, we use mu1 and mu2, but remember we're finding differences here. So really it's just mu d.
Oh, so mu d is what, greater than or equal to?
Mu d is greater than or equal to 5. That's right.
Oh, okay, I got you.
Because they say at least 5 pounds.
So it's just numerical.
Yep. Now, which would this be then? Would this be the null or the alternative?
That's a null.
That's the null if you're AP. If you're dual credit. If you're AP, what should this be changed to? Equal. Yeah. What would the alternative be? Mu d is less than 5. Perfect. Okay, and what's mu d? Well, I'll give that one to y'all because I don't think it says in the problem. Mu d is the mean of individual weight changes. So we have this center that claims they'll lose at least 5 pounds in the first week. And after numerous complaints, the state's consumer protection agency saying, yeah, right, let's prove it. Let's prove you're wrong. False advertising. That's essentially what they're after here, false advertising. The center's advertising at least 5 pounds during the first week. People are saying it's not happening. They're making false claims. So now the state's having to step in and say, well, let's see. Let's do our own study and see if there could be some false claims going on. So what else does just the problem give us without looking at the data? Alpha. Alpha has to be what? 0.05. So let's make note of that. What else?
N equals 12.
N equals 12.
That's
Yeah, that's about all from the problem itself, but that's still part of it. We know the hypotheses, we know alpha, and we know n. We haven't even looked at the data yet. So let's do that. There's our data. So what we need to do is we need to compute, since this is paired data, they weigh in and then they weigh again after 1 week. So we need to compute the difference in their weight. For just the differences, you may be able to do this in your head. So we're just going to do their initial weight minus the 1 week weight. Yep. On the 84, it does the same. Like if you go into put the data in and you just type 195 minus 195, enter, it'll already put the 0 entry in there. Yep. It will do that, yes. If these weren't integers, that's probably what I'd do. Since they're integers.
What are the integers?
Whole number. Was, I think I'll just turn these in, but.
That's the reminder to go first.
Yep.
Okay.
Okay, so what is 195 minus 195? 0. So the first weight change is 0. 153 minus 151. 2. 174 minus 170.
4,
Yep. What about the next one?
2,
Next.
5,
Next.
3.
Okay.
You know,
Yeah.
4. I got negative 1 on the next one.
That's all right.
1, 6, 4, 1.
Good. So now we can actually put those into into list 1 and do one variable stats on them. We already said n is 12, so y'all don't have to tell me that number. But I will need xd bar and sd.
Oh, and we're looking for XD bar and then SD bar?
Yep.
Or SD,
Yep.
And we do the bar stat?
Yep.
XD bar 2.33.
2.33.
We don't gotta do anything with repeating, right?
For what?
We don't have to do anything with repeating.
No. We just said 2.33. What about SD?
2.67.
2.67. Okay, so that's what they did on this slide. They found the differences. And they did the hypotheses. Okay, so next step is assumptions. They wrote a paragraph. We don't have to write a paragraph.
Wait, so we just had to find the X bar and the S? On the weight loss one?
Well, the next page also continues it.
Oh,
Yeah.
my bad.
But what I was saying was for assumptions, they wrote a whole paragraph. I'm not wanting y'all to write a paragraph. I don't want to write a paragraph.
I appreciate you.
So, I'll write kind of around it what we need to write, and then we can go from there. So don't start trying to copy this paragraph unless you just really want to. So what I did was I just said, okay, number 1, is it a random sample? So look back in the problem. What's it say? Yep, they chose 12 random subjects. So all I said here was yes, it's stated in the problem. Okay, second assumption that we've got to verify. Do we have a large sample? No. Where'd my pen go? There it is. So, large, no. N equals 12 is less than 30. We must verify normality.
So is that the next step in case that it's smaller?
Yep. So we do that, and if we do a box plot, we'll notice that the box plot has one outlier. Like, okay, well, this part's roughly symmetric. I mean, roughly symmetric. But we have one outlier. So I know I'm writing these where this would come in, you would draw your plot and then say, notice it's roughly symmetric with one outlier. However, we can still assume normality. So it's still safe to assume normality.
So you want us to draw these?
You don't have to draw the normal probability plot. I would like you to draw the box plot. So it's safe to assume normality. Now, when we look at this box plot and we see that one outlier, I mean, if we had like data software just at our fingertips and we could run another plot, it would probably be a good idea to do a normal probability plot just to see, okay, wait, I have an outlier. Is this really still safe to assume normality? If you look at our plot, notice that yes, it's along a straight line, but this one outlier that's away from everything else kind of pulls the tail of our line up. If it wouldn't be for this one, we would have a pretty darn straight line coming through here. And we would all be pretty close to the line. But that one outlier kind of skews us a little bit. But it's still safe to assume normality. So, and just from personal experience, I mean, when on this weight loss journey that I'm on, when I go to lose weight, about a week before, my weight will actually spike and then drop lower than what it was. So, yeah, it'll spike up a little bit and then drop. And so, and in that time, I'm like, my gosh, I'm gaining weight. And then boom, I'll drop. Oh, okay. I guess I was holding on to that water. Anyone still trying to get this slide written down? No? Okay. Next, I don't want these calculations up here. Go away. So just a reminder of what our values were for the mean. X bar D. We got 2.33. For the standard deviation, we said it was 2.67. For N, we said it was 12. And what did we say alpha was? Good. Okay, so we don't need it to calculate the test statistic. We will need it here in a second though. Based on our N, what's our degrees of freedom?
11.
11. I'm sorry.
So we're back at the N-1 for the group two.
We're back to the N-1 for this section, yes.
And what is the other one for, the other equation?
Are you talking about that V equation that we were doing? That's when we had the difference of means. This is paired samples. There's still difference of means, but we have dependent samples this time.
Okay.
Independent, that's right. Okay, so let's get our test statistic. So T equals, I'm going to go and write down the formula. That way we know what to plug in and where. Okay, so our X bar was 2.33. Now, this example is a little bit different because are we subtracting 0 here? No. Our null, remember, I'm going to write the dual credit version, was that mu d was greater than or equal to 5. The alternative was that mu d was less than 5. So we're not going to use 0 here like we have been. We're going to have to use 5. SD we said was 2.67, and then we divide that by the square root of 12. So if we calculate this, what would we get? Negative 3.46. Yes.
Was there a problem that on the mean difference when trying to solve for T, was there one that's like similar to this problem?
There should have been. What do you mean by similar to this problem?
Like basically instead of 0 you put some other number?
I can't remember exactly, but I'm sure there probably was. Was it a specific problem? I could check right quick for you if you remember the specific problem.
No, just wondering if there's questions similar to like this.
Okay. So we've been kind of just dragging dual credit through this. We're doing it the AP way. We're doing it the AP way. On my notes, I have it the AP way, but what about we do it y'all's way today? Does that sound good? Where we do the critical region? Cool with that?
That'd be very nice.
Okay, we'll do that. Third period, ask for it, and I just was gonna mention it and then say, but we're doing it the AP way, and they're all like, say, you don't do anything our way. I said, fine, I'll do this one y'all's way. So, okay. So we found the test statistic. Now, according to how dual credits problems work, we need to get the critical value. So, what kind of test do we have here? Left-tailed, right-tailed, or two-tailed?
Oh, it's left tail, right tail. You follow the alternative.
You follow the alternative, that's right.
Left tail.
This is going to be left-tailed. What's our significance level?
0.5.
Yeah, so our T critical, we're going to need to look at a one-tailed test.
Oh, see, dang it,
Alpha is 0.05.
I know exactly what 0.5 is. Sure. Negative 1.645.
And how many degrees of freedom do we need? 11. So if I look up 11 degrees of freedom, a one-tailed 0.05, 1.79, well, we're left-tailed, so it would need to be negative. Negative 1.7, you said 96?
Yes, it was, so let me check.
Go back.
Yeah, negative 1.796.
Okay. So what would our rejection region be? I'm going to just put that over here as RR. If T is less than negative 1.796. Okay, well, we have our test statistic. It's negative 3.46. How does that compare to our rejection region?
Reject.
It's in the region, so we reject. So we reject H naught.
Is this the conclusion?
Yep, now we're going to the conclusion. That's right. Since T is in the rejection region. Like I said, AP, you may want to make a note to say this is a different method than what y'all are using. This isn't the p-value method. Yep, this is a different method. It's just, I wanted them to see an example of their way. That way when they look through the notes, they have a point to reference. So, reject H naught since T is in the rejection region. So, since we reject, which one was the claim, the null or the alternative?
Claim was the alternative. Wasn't it? I thought it said it was not at least.
It's the null. The claim was.
Claim, yeah. I meant like what they were trying to prove. Let me go back to what I was saying. Yeah, see, I was talking about where it says where the consumer protection is in Dallas this morning.
Yeah. Well, yes, right. It says in the last, determine if there is statistical evidence of the weight reduction center's claim.
Okay. Yeah, I got you. I'm bad.
So their claim is the null. So what if we're rejecting the null? That means there is sufficient evidence would we be supporting or rejecting the claim? Remember, our claim is H naught.
Oh, reject.
That's right. There's sufficient evidence to reject the weight loss center's claim. Yep, their claim was false. They had some false advertisement going on. Okay, questions on this example? No? Okay. So maybe for this section, you'll credit, maybe you want to put a note to look at this example, because this example is how y'all will do it. Okay. Now, we already talked about that. Now, if we look at the output from Minitab of the data, which Minitab, remember, is a statistical software, what do you notice about their t-value, which is the same thing as their t-statistic? What do y'all notice about that? It's roughly the same. If we would have done AP's method and did p-value, that should have been our p-value. So this test that we just ran, the statistical software will do it for you with like one line of code. But with that being said, we would have to still make the same assumptions. So that's where those graphs that you saw, the box plot and the normal probability plot, that's like if you're sitting down to look at a set of data, you would run those first to be like, okay, yep, that looks normal. Okay, I can proceed. I don't have to look into anything else. It's normal. Questions on 11.2. Okay, 11.3. Large sample inferences concerning two population proportions or treatments. Okay, this example that we're going to focus on today in this section to me is kind of interesting. I wonder if it really does work. It's gross but interesting at the same time. Okay, so we're going to kind of set the stage with an example, but then we're also going to do a hypothesis test later on at the end of class with this same example. So evidently some people tend to think duct tape can literally fix anything, even remove warts. So investigators at Madigan Army Medical Center tested using duct tape to remove warts versus the traditional freezing method.
You just put them on there and rub them off?
I think maybe you do is you put it on there and you leave it for a while.
Yeah, that's what when I saw that, I'm like, that sounds interesting. And then in our example we're going to work, it actually says you put it on, leave it on for 6 days, take it off, soak it in water, and then file it down with the emery board.
I think that's it's like a or something you're supposed to. Yeah, I knew they had. in like elementary or whatever, and they had to put this game on some identity and leave it on there for like 6 days. And I took it off. So I think people just looked up.
Well, I mean, we are talking about the Army, so. They probably keep duct tape in their bags. Something breaks, slap duct tape or WD-40 on it. Okay, anyways. So, for us just setting the stage, let's suppose that duct tape treatment will successfully remove 50% of the warts and freezing removes 60%. Let's investigate the sampling distribution of p hat from freezing and p hat from taping. So, of course, P of freezing is the true proportion that are successfully removed by freezing. And we say P of freezing is 0.6. Similar concept for taping. P of taping, the proportion that worked for taping is 0.5. So let's suppose we treat 100 warts using the traditional freezing method, and we calculated the proportion of warts that are successfully removed. We did that over and over and over, we would have the sampling distribution p hat freeze. And our standard deviation for that, we would have a mean of 0.6, a standard deviation of 0.6 times 0.4 over 100. Well, the square root of that, anyways. This one's about, I need to go to the next one. It's going to go away, but then once I get 2 more advances on this slide, it'll come back. So I'm about to hide the left side for a second, but don't worry, it's not gone forever. It'll come back. I just want to talk about the right side. So if we do the same thing with duct tape, we treat 100 warts over samples of 100 over and over and over. Then we get the proportion of warts, the sampling distribution, of that proportion from tape. We would have a mean of 0.5 and a standard deviation equal to the square root of 0.5 times 0.5 divided by 100.
What does that sigma say under it?
It says p hat tape.
Okay.
Yep. Okay, see, told you, left side would come back. I just needed to advance it. So if we randomly take one sample of the proportions for the freezing treatment, one sample of the proportions from the duct tape treatment, and we found their difference, that would create its own distribution. So if we did that over and over and over, we would get the sampling distribution of p hat freezing minus p hat of taping. So where did this 0.1 come from? Well, we just did 0.6 minus 0.5. That got us 0.1. And then our standard deviation is the square root of the sum of both variances. Okay, so let's look at some properties of the sampling distributions. So the first property, well, let's back up. So if the two random samples were back to being selected independently, if they're selected independently of one another, then the properties hold that the mean of the sampling differences is equal to P1 minus P2. So the mean of the sampling differences of the proportions is equal to just the difference of the population proportions. This is saying that we have an unbiased statistic for estimating the difference, the true difference in the sample proportions. Also, sigma is equal to this lovely beast that we won't even get to use. We're going to have to use a different beast.
Which one's better?
Being that the different beast is the one on your formula chart, I would say the different beast. I'm not sure if it is or not. Yeah, y'all probably do, honestly. Probably so, but let me check. Come to the dark side. We have cookies. Actually, y'all do not have to memorize it. It's on y'all's formula chart. Both versions are on y'all's formula charts. Y'all actually have both versions. They only have one version. So. Yeah. Most of y'all's formulas, though, are on the chart. You just have to know how to piece them together. They're not pieced together. Yep. Give you the building blocks. You have to build it, though. It's a kit that comes from IKEA, basically. Yeah. Yep. Okay, so the reason that we're not really going to get to use this formula much is because do we typically know the population proportions? Not really. Since they're unknown, we're going to create a common value for the proportions. We're going to estimate them. So what we're really going to use is this formula up here for P. So any place you see a P in our formula down here, it can be summarized using this one single P. P bar. That's the P we're going to use instead of P1 and P2.
Do we need to write down the P-bar? Is it anywhere?
You probably need to write it down. It's not on your notes.
Instead of P1 and P2, use P-bar?
Yep.
So like P-bar 1 and P-bar 2, or just one?
There's just one P bar. It's a common P, common value. Because if you notice in P bar, we're going to use the estimate for P1 hat and P2 hat. So we're using these estimates already to create this one common estimate.
Okay.
And I put both versions because depending on what the problem gives you would depend on which version you use. If they give you P hat 1 and P hat 2, then you'd need to use the first one. Now I actually kind of changed this to favor dual credit. P bar is what's used on y'all's formula chart. So I changed it to reflect that. AP, instead of saying P bar, they say PC for P common. That's the only difference, but.
So anytime we do this, we replace P1 and P2 with P bar.
For the sigma. When calculating sigma, yes. Don't do it in the top.
We're calculating the sigma P hat 1 minus P hat 2.
Yes.
Okay.
And we'll see an example and I'll show y'all how to do it. Now, our other one is that if both N1 and N2 are large, meaning N1 times P1 is greater than or equal to 10, N1 times 1 minus P1 is greater than or equal to 10. Same story for N2. They're both large. The P1 hat and P2 hat each have a sampling distribution that's approximately normal, which means their difference has a sampling distribution that's approximately normal. Okay, can I go to the next one? Will, are you done writing the slide? You are? Okay, let's sure. Okay, next page. So let's talk about our hypotheses. So the null hypothesis is that the difference in the means is 0. Or sorry, the difference in the proportions is 0. Or if you're dual credit, greater than equal to or less than or equal to. The test statistic is this lovely thing. It's really not that bad. So P1 hat minus P2 hat. These stay, These stay as P1 and P2 hat. Don't try to do P bar here, it won't work. The only time you use P bar is down here in the denominator, down in the numerator. Don't think it works like that. Down in the denominator.
What is Q bar? Is that like 1 minus Q bar?
That's exactly right. You beat me to it. Good job. 1 minus P bar. I was actually just about to ask y'all that.
Wait, does P bar replace P1 P2 up there?
In the standard deviation, it does.
But the one subtracted from that, the one minus.
That's our hypothesized value.
Uh,
Is that what you're asking, this one?
Yeah.
This comes from the hypothesis.
We get so lost in the notes until we get like to an example.
Yeah. Yeah, that's I hate to say that's really the only way in math you learn stuff is with examples. At least for me. That's just from my experience. Like,
It's hard to listen to like notes and all that and then not be able to like try to work it out.
yeah. Or just theory, it's like, okay, this is all theory, this is all definitions, blah, 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 blah.
Exactly.
Oh, example. Okay, let me see if I can do it.
Exactly. Like, let's see what I can figure out.
Yeah, I'm the same way. That's why I struggled in proofs-based classes in college. Okay, so in our formula here, P bar, we use that formula we wrote down earlier. So x1 plus x2 over n1 plus n2. So we'll use that. Now for our alternative hypotheses, they're the same ones that we've been using. You can have the difference be greater than 0, and that's the area to the right. So that means this is a right-tailed test. If it's less than, what kind of test would it be? Left-tailed. And if it's not equal to, then it's a two-tailed. So the same hypotheses that we've been using. There's another way to write these statements, though. So you could say that, well, I'll say you could say, our original way for the null is that P1 minus P2 equals 0. That's the original. What I would do on these is create two columns. Have the OG, and then the new. I'm going to put new in quotes because it's not really new. We've actually seen this before. So the other way I could write the null is that P1 is equal to P2. So this can turn into that. Now that you hopefully got it set up like this, based on what I wrote, it's going to fade from the old to the new. So it won't be in two columns anymore, unless I physically write it. So what would this one turn into? P1 is greater than P2. So this is the original, faded into the new. Or it will soon fade into the new. There it goes. What would that one turn into? P1 is less than P2. And then last but not least, not equal. What would this one turn into? Does not equal P2. Good. So make sure you define what both P1 and P2 are. Not only for if your AP when I'm grading your paper, but also for your own sanity. You need to make sure you know what each one is.
You said this was a to the bell type day?
Yeah, this whole chapter, unfortunately, is like a to the bell chapter.
Alright.
Because we have, remember, this packet's 20 pages long, and we have 5 days to cover it.
Yep.
So that's 4 pages a day.
Gotcha.
We may have maybe a minute or two today. Okay, so let's look at our assumptions for our large sample z-test. The samples have to be independently chosen random samples, or the treatments were assigned at random to the individuals or objects. Also, both sample sizes have to be large. Night. Okay, so both samples being large, that means what we said earlier. N1 and P1, N1 times P1 is going to be greater than or equal to 10. Dual credit, we haven't used 10 this semester, we've used 5, and then 30, yeah. If it's for means, we use 30. For proportions, we use 5. Of course, if it's bigger than 10, that means it has to be bigger than 5. So, luckily, we haven't had an example where it's like, oh, it works one way, but not the other. It's been.
Is that a thing that works one way or the other?
What's that?
Is that a thing that works one way and not the other?
Well, I mean, if we're bigger than, if we're like 8,
Oh, okay, I got you.
it would work for y'all, but not not for AP. So, okay. And then for the second sample, we have to have the same thing. It's everything's got to be greater than or equal to 10 or 5. So those are our assumptions that we have to look at. Since P1 and P2 are known, since they're unknown, we must use P1 hat and P2 hat to verify. Usually we want to stick with P, but we can't. We don't know P. That's why we're having to do that whole P bar deal. We don't know P. So you must use P1 hat and P2 hat to verify. And now the time you've all been waiting for. Since we finished that first example, the time y'all are waiting for the next one. Now y'all are ready for one.
At the very bottom of the page.
Good news is on Monday, most of our stuff will be examples. There won't be many that aren't examples.
Good.
We'll have 4 examples and a little bit of definition. Okay, we ready for the example? Anyone still trying to write anything down? Let's go. Back to talking about warts and duct tape. So the patients with warts were randomly assigned to either the duct tape treatment or the more traditional freezing treatment. Those in the duct tape group wore the duct tape over the wart for 6 days, then removed the tape, soaked the area in water, and used an emery board to scrape the area. The process was repeated for a maximum of 2 months or until the wart was gone. And they give us the following data. So does the data suggest that freezing, my voice just cracked, freezing is less successful than duct tape? So let's use this sentence before we even look at anything. Let's use this sentence to help us formulate our hypotheses. So freezing, we're going to use as population 1. So P1. Duct tape, we're going to use as population 2. So this is saying, is freezing less than duct tape? Which hypothesis would this be? Less than 0, but which one is that? Is that a null or is that an alternative? That's an alternative. So this is our alternative, which means the null is P1. For y'all, it would be equals P2. For dual credit, P1 is greater than or equal to P2. Now I'm actually going to go to the next slide where this is written on there. So they wrote a whole paragraph defining what P1 and P2 are. Again, let's shorten it. I don't like paragraphs. I know y'all don't either. So P1 is the true proportion of warts removed by freezing. P2, so you don't have to write this paragraph when defining it. You can just write what I'm writing. P2 is the true proportion of warts removed by duct tape. And notice that these hypotheses are just really rewritten in the original form from what we had earlier. So, same hypotheses are just written in a little bit different way. So now that we have the hypotheses, what's the next step? Assumptions. So, do they come from a random sample? Yeah. They're randomly assigned. So yes, they are random. And then now we have to check, is the sample large enough? Well, we can't do that on this one. We're dealing with proportions. So we have to find P1 hat and P2 hat. So how do I get P1 hat? 60 divided by 100, which is 0.6. P2 hat, which is the 2 decimal places. Yep. 0.85. Okay, so we've got to check. Is N1 times P1 greater than or equal to 10? So 100 times 0.6 gives me what? 60. Is that greater than or equal to 10? Yeah. What about N1 times Q1? So it's going to be 100 times 0.4, which is 40. Is that greater than or equal to 10? Yes. So that meets our requirements. Now let's check the second population. N2 times, sorry, these should be hats right here. N2 times P hat 2. So 104 times 0.85. That gives you, yep, it's roughly 88. We rounded this 0.85, so it's going to come out to 88.4, but yes. If we wouldn't have rounded, it'd be exactly 88, which is bigger than 10. Then we have N2 Q2 hat. It's going to be 104 times 0.15, which equals, what's that? Should be 15.6. Is that bigger than or greater than or equal to 10? Yes. So are our samples large enough? Yes, they are. So from here, we can actually proceed with our test statistic. Okay. Oh, wrong way. So we've got to get P bar. Because remember, we need P bar to do the standard deviation. So P bar, we do x1 plus x2 over n1 plus n2. So 60 plus 88 over 100 plus 104. That's going to be 148 over 204. Which, if we did this 5 decimal places, we would get 0.72549. So to 5 decimal places, we get 0.72549. Okay, we've got our P bar. Let's go on and calculate Z. So Z equals, well, we're going to need P1 hat minus P2 hat. So 0.6 minus, we said earlier it was 0.85 minus 0 over. Then we take the square root. I'm going to round this because I don't have much room here. I don't want this to drag on forever. So 0.7, I'm going to say 726. That's P bar. 1 minus P bar would be 0.274. Times 1 over N1 plus 1 over N2. So if you calculate this, what do you get to 2 decimal places? Negative 4.00, right? Okay. There's our test statistic. Now, we're going to use the p-value method, but dual credit, you have one problem on your homework that uses p-value method. So this is still valid for y'all too. Most of the problems use rejection region, but you have one that does p-value. Because we're doing Z. So we have our Z table. Okay, let's remind ourselves of the hypotheses. Well, let's remind ourselves of the signs. For H naught, we said greater than or equal to. HA was less than. So this is a what kind of test? Left-tailed. So for the p-value, we need to find the probability that Z is less than -4. Well, let's look at our Z table. Can we find -4 in the Z table? No. Why not? Didn't go that low. If it did, it'd be like 0.000005. We can say it's approximately 0, yeah. So we can just stop right here and say approximately 0. So even if alpha was the lowest one we've used, even if alpha was 0.01, what would our decision be to still do? Or reject the null, yes. Reject H naught. Which one was the claim? Which one? Alternative, that's right. So we could say there is sufficient evidence so this would go under the conclusion at this point. State the conclusion. There is sufficient evidence to support the claim that freezing is less successful than duct tape. I could add in removing warts, but I'm out of room. So, okay, so for now, notes-wise, this is it. I do want to do a little activity, or not activity, but a little diagram with dual credit to kind of help. Because third period was like, how do we know whether we support or we reject, or there is evidence, there's not evidence?
Where can we write this?
So you could probably, if you write small enough, you could probably write this on the bottom of the last page.
Okay.
Okay, so let's draw a box. I'm gonna write it large, but I wouldn't draw it too big because we still have an example on that page. Let's do a box with 4 boxes in it, smaller ones. On top, we're going to have where is the claim. So if the claim is the null, or if the claim is the alternative. And then over here, we're going to have the decision we make. So what are our 2 decisions? Well, we could reject H0, or we could, I'm going to abbreviate, we could fail to reject H0. So if we reject the null and the claim is the null, then what are we saying? There is, I'm going to abbreviate sufficient. There is sufficient evidence to reject the claim. The claim is the null and we just rejected it. So there's sufficient evidence to reject the claim.
Next one would be what, sufficient to support
For which one?
for the H of alternative?
Right here?
Yeah, or to be insufficient to reject.
So this one, if the claim was the alternative,
Maybe insufficient.
there would be sufficient evidence. There is to support, that's right. There is sufficient evidence to support the claim. Yeah. Now let's go down below. So the claim is the null, and we fail to reject the null. So this one would be there is insufficient. That's right. Or you could say there is not sufficient evidence to reject the claim. Now, if the claim's the alternative and we fail to reject, we would say there is insufficient
Support.
evidence to support. That's right. So does this chart kind of help clear up some of the confusion? I was trying to actually, it was kind of a funny story. I came up with this on the fly last period because my computer started freaking out on me and I couldn't research it to give an answer. I'm like, you know what, let's just do this. I hope it works. And then they're like, why couldn't we have done that 2 weeks ago? I'm like, well, I guess it worked. It worked. Sweet. I think I'm going to take a picture of this myself, so I'll have it.
So, are we going to
Yes, ma'am.
back to the other weekend?
You too.
For this problem, once it's been instructed 95% for 8,
Uh-huh.
does that mean to use those things, or do you consider one for this?
For which part?
The
I don't know what to say.
It says construct and interpret a manufacturer's consumable compensable for the difference between the mean on the daily profile and the mean on after
Yeah. For women.
Oh, yes, I've read this 3 times now, and I always thought it said for male and female.
Olivia and Will, I forgot to give y'all these. It's graded papers. I forgot to give them to y'all. How'd y'all cover it?
Pretty well. The sound was doing something weird last night, but
Gotcha. It's the first time.
yeah, exactly. Thursday night's always the test.
Is that one of y'all's calculators?